Good evening. My name is Dr. Darrell Boyd, and I'm coming to you on behalf of the Transformational Education Adventure Center, which is also known as the T Center and is located in McLean, Virginia. And I'll be teaching a STEM lesson. Tonight, our STEM lesson focuses on something called Newton's Cradle. Newton's Cradle. And that name Newton is in reference to the great scientist, Sir Isaac Newton. And Sir Isaac Newton is responsible for a number of principles and laws in physics that we are very familiar with in today's present time. And so with that, I will introduce to you something you've probably seen before but didn't know what it was called, the Newton's Cradle. All right, so Newton's Cradle is a series of steel balls that are attached to a string, a single string. Notice that there's a single string, and each ball is attached to a string that goes from one side to the other, one single string. And there are, in my particular Newton's Cradle, there are 5 of these steel balls. All right, you'll notice that the 5 balls are in very close proximity to one another. And the concept that Newton's Cradle actually presents includes the conservation of energy and the conservation of momentum. All right, conservation of energy and the conservation of momentum, which in general, in the simplest terms, what this means is that energy is not going to be created or destroyed, but rather it's going to be transferred, okay? So there'll be energy transferred from one ball to another. Now, I will tell you the explanation of what Newton's Cradle actually does from a physics standpoint cannot be fully explained simply by explaining conservation of momentum and conservation of energy. And in the case that I'm presenting today with 5 balls, you really can't describe it that way with 5 balls in the most exact terms. But it gives you a good idea of what would happen if you were talking about one ball hitting another ball under very specific circumstances, all right? So with conservation of momentum, what we mean is that the momentum from one ball is transferred into the other, okay? Just like energy is being transferred. So it's not being created or destroyed, but it's being transferred, all right? And we will see that as we do this. So this is really a fun demonstration to do, and let's give it a go. So what do I mean when I say that energy is going to be conserved? What I mean is, well, I'll ask, what do you think is going to happen? I take one ball and I lift it up here, and it's going to crash into the ball that's next to it. Will the ball cause all 4 of these balls to move? Will none of the balls move at all? Or will the ball that I drop just bounce back? What do you think? All right, let's give it a shot. All right, so you'll notice just one ball comes off the end. They don't all 4 balls move when I just drop one ball. So I've taken one ball and I dropped it into another that is connected to another, another. And instead of all 4 of these being moved, only the ball on the end moved. So what happens if I take 2 balls? What do you think is going to happen? Will all 3 of those balls finally move, or will just one ball move as in the first example, or will just 2 balls move? Or will they stop moving? What do you think? There's a lot of options here. Here we go. All right, you'll notice just 2 balls bounce off the end, and the ball in the center stays reasonably stationary. All right, I'll do that one again so you can see it. All right, pretty cool. So instead of all 3 of these balls moving, just 2 move. And remember, I only pulled 2 back. So what happens now? I'm going to take all 3 of these balls here, and crashed them into these two. Now, if all of these balls are assumed to be the same weight, same size, it would seem like if I took 3 balls, they should easily move all 2 balls, right? What do you think? Let's find out what happens. 3 crashing into 2. All right, so notice what's actually happening is when these 3 balls hit 2, one of the 3 actually moves along with the other 2 that are on this end, so 3 actually come off. Remember, we're talking about conservation of energy and conservation of momentum. So 3 balls crash into 2, and instead of only 2 coming off, 3 of them come off, including one that initially was being pulled back. I'll show that to you one more time. All right. Now, what happens if I take all 4? Will just this 1 ball pop off, or will 4 balls come off this way, leaving 1 behind? What do you think? Give it a try. So, and I take all 4, it hits 1 ball, 3 of them go with that 1 and leaves 1 behind. All right. So 4 crashing into 1 gives me 4 crashing, going away, and 1 staying behind. I'll do it one more time just so you can see it. All right. Pretty awesome, huh? 4, 4, 4, 4, 4. All right. Now, let's have some fun with this. What happens if I take 1 from either end? All right. What happens if I take 1 from one side and 2 from the other? Notice how the center one is reasonably stationary because energy is being transferred through it on either side at almost the same time. What if I take 3 and 1? All right. Pretty awesome, huh? So what you learned from Newton's cradle is that energy and momentum are conserved, all right? And that is in the simplest of terms. Again, I do want to point out, because we're using 5 balls, because they are touching, this isn't, from a mathematical and physics standpoint, conservation of momentum and conservation of energy don't fully explain the motion that we saw, but they are encapsulated in the motion that we saw. And it's also a great way to just entertain yourself. All right, so if you ever get the chance, you can go buy Newton's Cradle like this for a few dollars. They're pretty cool, pretty awesome. Last thing I'll say is the balls are made out of steel, and that has a major effect on why it works so well in this particular setup. But as a law of physics, momentum and energy are conserved. All right, that is our lesson for today. I hope you enjoyed it. Hope you learned something, and I will see you next time.